We talk about DC motor losses. We've got those that we can calculate and those we can't. Okay. One of the big things on a motor, you can obviously calculate power in, right? Or measure power in. Okay, you've got your voltage and your amps. These two together will give you your watts in, right? Volts times amps will give you your power in. You can also measure your power out. Okay? We talked about horsepower, dynamometers, and measuring your power out. Okay? This is mechanical power, so we've got to measure that mechanically. So somewhere between power in and power out, we have a whole series of losses. Okay? What kind of losses do we have?
Copper.
Heat.
What's that?
Heat losses.
Heat losses. Okay?
Friction.
We've got heat losses. We have friction. Okay, we have windage.
Eddy current.
What the heck is windage? What is windage? And I don't want to
Winding.
answer that. What?
It's the winded winding, right? It's from the armature, the interpole, the air.
Windage is so simple.
It's basically like the kind of like the aerodynamic, you know, kind of like when a car is, you know, going.
Windage,
And
okay?
wind's
We've
pushing
got a
back.
motor. We've got a motor. It's spinning. Okay?
Okay. So that fan.
You've got a motor. It's spinning down here. You look at that motor. Right there on the end of the motor. What do we see down here?
Fan.
Fan. So if I'm turning a little bit, you have a little bit of loss because you got to turn that fan. You spin it a lot. The amount of power it takes to spin that fan increases, right? Why do we have a fan on the end of the motor? Cool the motor. Okay.
You're talking when you say windage, that's more of a air resistance.
It's the air resistance to the fan. Okay? Like with any fan, it takes power to push and turn the fan, right? Okay. You've got friction, you've got brush losses. Okay? Eddy current losses. Okay? And you have stray losses.
What would we count as our copper losses?
And you've got your copper losses. That's the big one. Now your heat, okay, somebody threw heat out there. That comes from multiple sources. Your heat's going to come from friction, it's going to come from some brush losses, come from eddy current, it'll come from stray losses, and it'll definitely come from your copper losses. Okay? We've got all those losses up there, and there's some of them that we can get in, we can calculate. Okay? We can calculate our copper losses. All of our copper losses we can calculate. Okay? Friction losses, windage, a lot of the, you can fire up your motor and take your fan out. Okay? So you can measure the before and after with and without the fan. You want to run it a lot like that, but if you want to look at this, you can measure it before and after. But basically what boils down is you have all of your copper losses that you can calculate and the contribution based on that. And then you have the rest of them, which all lump in. They're not going to change. The motor is running on a constant speed. All of these are fairly constant, but they are things that go into makeup of the motor. Okay? Your friction, you can't really change the bearings, but as the bearings get dirty, if you're not cleaning the brush out of the brush carbon out of the bearings, keeping them clean, your bearings are going to start to wear and your friction's going to go up.
They don't use sealed bearings in those?
They use sealed bearings, but the carbon can still get in there. Okay?
Yes.
The carbon can still get in there. You still have to get in and clean, keep them clean. Okay? Windage is not going to change. There's nothing you can do about that. Okay? Your brush losses. You want to keep the brushes set properly. Spring tension set right. Okay? Minimize your brush losses on there. Eddy current losses, you can't change those. That's how they make the machine up. Whatever they use to make the machine, all the laminations, that's under the motor manufacturer. Stray losses, whatever is left over, we can't really change that. Okay? So what you're looking at and measuring are your copper losses. Okay? You've got your copper losses. What kind of copper are we talking about?
Winding.
All your windings, right? What we're talking about are your I squared R losses. I squared R. What is I squared R also known as? Power. Okay? It's our power losses. Okay, what are our components? We have our armature. You have your series field. Your shunt field. Okay, interpoles.
Do you have a loss at the brushes?
There are loss at the brushes, but those aren't on the copper loss.
Okay.
Okay? Okay. You have all of these items on here that we have to worry about. Calculate. Armature, you've got RA for armature. RS for series field. RF for the shunt field. RI for the interpoles. Okay? And we just use our I squared R. Okay? IA squared. Whatever you've got the current through the armature, you square it. That's your power. Is it okay if I swap those two around like that?
Yeah.
I squared R, R, I squared?
Yeah, why not?
Okay. I squared RA. That better? Same thing, right?
Yes.
Okay. RS, RF, RI. Okay, series field. What is the current in a series field? Same as the current in the armature, right? When it's connected up. IA squared, right? Shunt field. Whoops. Okay. And on your interpoles, okay, I'm going to change both of these back over to IS squared and interpole squared. You're just talking about the current that goes to that device. The current through the series and the interpoles may or may not be exactly the same as the current going through the armature, depending on how you have it connected up. Okay? All right? So we go through this. You keep in mind that what you're looking for is I squared R. I squared R, I squared R, over and over and over again for all of those. Calculate your power. Okay? If you have, you've got your power. Okay. Got power in, right? Now if we subtract our copper losses, okay, we subtract our power out, what we're left with are our stray losses, brush losses, eddy current losses, all the other mechanical type losses. Okay, so what we're going to be doing in here, these are the items you're going to be calculating. Power out, copper losses, power in, and what the remaining losses are. All of those other losses, eddy currents, brush losses, friction, okay, they're all going to be lumped into here. Okay, we can calculate copper losses, right? Mm-hmm. I squared R for everything. We can calculate power out through the use of a dynamometer.
That'll just be total losses of the rest?
Okay. This and this are your total losses.
Yes,
Okay?
recognize.
Your copper losses and your remaining losses. What we're doing is we're bunching all of those other losses into one big thing. Okay? We can't get in there and measure our copper, our brush losses. We can't measure the eddy current. What's that?
We're never gonna measure all the other losses?
No.
It's just whatever's left?
Right. Okay. And hopefully, if the motor is efficient, their contribution will be so small, or a very small part of your losses. Okay? You're going to find that our copper losses should be a large contribution to what we're measuring. Okay?
Do they tell you an efficiency rating on its stamp?
There's a nut on this. There's
But
not an
what for?
efficiency. You can calculate what the efficiency is. You can calculate nameplate power in.
Mm-hmm.
Okay, it's got power in, right?
Okay.
You got power out, so can you calculate the
Yes.
efficiency on it?
Yeah.
Okay.
I just didn't know if it was given to you.
No.
As part of
When
the
you
package.
purchase a motor, there may be, super E, super efficient, and with efficiency ratings, but in this case, there's no efficiency stamped on it.
Okay.
Okay? All right, we doing okay with this?
Yes.
Falling asleep yet? Okay,
Not yet.
so. All right. We have, I'm going to go through here real quick. Real simple here. We have a shunt motor. We have 240 volts applied. Armature resistance of, let's say, 0.05 ohm. Shunt field resistance of 250 ohms. Okay? And we calculate armature current, right? IF Okay, and we've got our total current. What are we missing here? We're missing something else here. If we're operating at full load right now, we're missing something. We talked about this yesterday.
The rated amps.
What's that?
The rated amps.
We're missing our count, the rated amps or the rated horsepower. Right. Number of things here. Well, let's just say we know what our counter EMF is on this, and we say it has, 215 volts counter EMF. Okay? Can you calculate all the remaining values? Should be able to.
Yeah.
Move that over, that's, okay. Let's go through this. Okay. We need to calculate the effective voltage on the armature. The armature is 240 volts minus 215 volts. Okay? Right. What do we have there? 25 volts?
Yeah.
Okay, 25 volts. Now our IA, going to be our effective voltage of 25 volts divided by our time, divided by the resistance there, right? E over R. 25 volts divided by 0.05 ohms. What do we have on that?
500.
What's that? 500? Woo! Must be a big motor, huh?
Yeah.
Okay. Shunt field, IF. Again, E over R. What E are we using in this point?
240.
240 volts. Divided by 250. What do we have for a current?
0.96.
0.96? Okay. Calculate our copper losses here. Okay. In this case, we've got 500 squared times 0.05 ohms. And over here we have 0.96 squared times 250. What do we have for I squared R in both of those? Okay, get that calculator out. What's that? Did I put volts instead of ohms?
You sure did.
Not yet.
Where did I do that?
Bottom of my head.
IF or RF?
Below it.
Bottom RF.
I put the, there you go. That better? Thank you. Okay. All right. Had the right number, the wrong units, right? Okay. Okay, what do we have for power on the armature circuit?
12,500.
1,500?
12,000.
12,500.
The locomotive engine?
What's that?
Locomotive engine?
1,100?
No.
230.4 watts.
230.4 watts. Okay? I'm not saying these are real numbers, but it's showing you just the process of calculating your I squared R, your copper losses. So these are two copper losses here. Copper loss in the armature circuit, and copper loss in your shunt field circuit.
Is there a way to put the counter EMF into like matrix type? Because like I'm trying to do it, and it just doesn't seem like it comes
Doesn't
out.
work out that well,
Yeah.
does it? No. Okay.